Alright, so today we're going to talk about how to solve systems of linear equations, but we're going to use matrices. So let's start with a simple example where we have three variables x, y, and z. And let's say we have 3x plus 2y minus z equals 1. And let's say you have x minus 2y plus z equals 0. I don't know how the numbers will look, but we'll try to do that. So if you were to want to solve this in terms of matrices, your first step is putting it into a matrix. So you're going to grab the coefficients in front of the x's. I'm going to put them as your first column, 3 and 1. Then if you have more equations, you just keep adding more. Now for your y's, you're going to pull 2 and negative 2. Those are the coefficients, so 2 and negative 2. Then z has a negative 1 and then a 1. And you're going to augment your matrix by putting a 1 or a 0. And a 0, not or. And that's going to be your first step. Now, if you wanted to solve the system of equations, and I kind of cheated, I guess, here, because what you would have normally done here, you just add them. And while that works, I'm going to go ahead and not do that. I'm going to swap the two equations first. So that is going to be reflected in my matrix form by swapping the rows. Why would I do that? Well, that is just because it will always be convenient to have ones in the upper corners. And I'm going to be more precise whenever I talk about what an upper corner is. That's going to be called a pivot. But I'm just going to, at the moment, swap my equations. So I'm going to do the corresponding thing here. So I'll just end up with the equation x minus 2y plus z equals 0. And then 3x plus 2y minus z equals 1. So that first step makes no sense when you're doing this, because you could just have added them. I'm not going to do it. What I did instead, I exchanged rows. And the way in a matrix that I'm going to denote that is by saying row 1 exchange row 2. Okay, so that's my first step. Why? Because what I want to do is in an upper corner at the moment, my top upper corner, I want it to be a 1. Why? Because whenever you have a 1, it's always easy to make everything below it 0. And that's going to be the first step I'm going to do to solve systems of equations. I'm going to make a 1 either by exchanging rows or by dividing by the coefficient. So I could have gone ahead and said here 1/3 of row 1 to divide. Why would I do that? Well, I would end up with a 1, great, but now I'd have a 2/3 and a negative 1/3 and 1/3. And don't let anyone fool you. Your math professor may tell you that they don't care, they can add fractions just as well as they add integers. Well, maybe that's them, but I can't. So I like having integers in as much as possible. And for as long as I can, I'm going to keep my integers. So if I can exchange a row to make a 1 in the upper corner, that's going to be it. That's what I'm going to do. So now what I'm going to do is want to make this one 0. So the way I would do it here is I would say the first row, I'm going to multiply it times negative 3. And then I would add them all. So I get negative 3 plus 3 equals 0. So 0 for x goes away. Then I get negative 3 times negative 2, which is going to be positive 6, sorry. I'm debating whether I'll write them. 6 plus 2. So I'm going to have the negative 3 times negative 2 is 6 plus 2. That's going to give me 8y. And then for z, I'm going to have negative 3 minus 1. Now that you know how it happens, you get negative 4z. And then you would have negative 3 times 0 plus 1 equals 1. So in the matrix, this would be translated into saying row 2 minus 3 row 1. And when you do that, what that turns into is, well, you copy your first row, and then you do 3 minus 1, 0, 2 minus negative 6, because it would be negative 3 times negative 2. So it's going to be 2 plus 6, which is 8. And then you have negative 1 minus 3 times 1, negative 1 minus 3, negative 4. And then 1 minus 0, 1. If you notice, that's what we got here, 8y minus 4z equals 1. But it's much easier when you do it and much more compact when you do it for matrices. That's why we favor the matrices. So now that I have that, the next step in my algorithm would be ignoring this row because I already did zeros below the pivot position. So what you do is you call this one a pivot, the top leftmost non-zero position, you make it a 1, and that 1 then you make zeros below it. So now you ignore this row and you look for the leftmost non-zero column. What is that? It's going to be this, the column where you have that 8. That's going to be your new pivot. Now I could have a 0 here and then this would be my pivot. But since I don't have zeros, this becomes my pivot. As I told you, I always will favor having a 1 in the pivot position. And why is that? Well, because right now I already have my equations as x, I wonder if I'm going to fit it, minus 2y plus z equals 0. And the next equation is just that 8y minus 4z equals 1. So what I want now is to turn this into a 1. And so what I'm going to do, I'm going to say, well, I cannot swap with any rows because I'm ignoring this one. This is the only row I have. So I'm going to make it at 1/8 of row 3. Row 3, row 2. Suddenly we have an extra row. Let me write that here back. Row 2. There you go. And now the matrix that we obtain is going to be copy the first row. This is going to be a 1 or negative 1/2 rather, and this is going to be a 1/8. At this point, I cannot avoid fractions despite what I told you earlier. You have to do it, so, well, you wait until the very last moment, and once you have your fractions, well, you deal with it. All right, so let me go ahead and erase this. I'm going to copy these two things above, ignore what we did, and we'll continue to try to solve this system of equations. And you say, this looks extremely complicated, but the matrix, whenever you do it with matrices, is a lot faster. So I'm going to copy, and I'll be right back. All right, so at this point, what we're going to do is, well, we know now that I have my pivots, 1 and 1. So all the pivots, you want to make them 1, and you want to make zeros below. When you get to this point, this matrix is what is called in a row echelon form, but it is not reduced row echelon form. So what you want to do to get it in reduced row echelon form, which is how we're going to read our solutions, you're going to make zeros above the pivots as well. So I only have one position that I got to get rid of, make 0, let's say. And the way you would do that, you would just add 2 times of this 1 to this 1 to make it 0. So what you're going to say is you're going to have row 1, and you're going to be adding 2 times row 2. All right, and we will, at this point in this equation, we're kind of a little bit lost. It's a lot easier to do it in matrices. So in this case, I'm going to do 1 minus 0, or plus 2 times 0, so it's 1. That's the beauty of the algorithm, the Gaussian elimination is called, that whenever you make zeros below, then you don't affect your pivot at all, so you start keeping those solutions. So now you're going to have negative 2 plus 2 times 1, so it's going to be 0 as we wanted. Then you're going to have 1 plus 2 times 1/2, which is going to be another 0, and then 0 plus 2 times 1/8, sorry, which is going to be 1/4. And now the next one you just copy. So in this case, what you would have to do is exactly the same. You'd have to add 2 times this row. But at this point, I'm going to abandon the equations. I'm just going to focus on the matrices, because from here, the matrix really is superior to read the actual solution. What happens is I have these pivots. I don't have any more. So whatever column I have on the still left-hand side of the equal, For example, this one, that's going to be this variable, which corresponds to z. When I call that variable z a free variable, meaning that I cannot get rid of that z, I cannot find a value for it, so I have to just use it for my solution. So z is going to be there regardless. So if I rewrite these equations, what I'm going to have is x plus 0y plus 0z is going to be equal to 1/4. So for x, I got a number, fabulous. But for y, I'm not going to get a number. I'm going to get y, oh, I forgot to write minus. Not very clean. No, not at all. Let me erase. Minus 1/2 of z equals 1/8. So at this point, since z is a free variable, I'm going to add it on both sides. And I'm going to obtain that y, I'm going to add this term, is equal to 1/8 plus 1/2 of z. And then what I can do to write this solution in parametric form is I can give z a name of a parameter. So if you want to write this, then I get x is 1/4, y is going to be equal to 1/8 plus 1/2 of t, and then z is t, which this corresponds to a vector solution. Let's write x as a vector with coordinates x, y, z, if you will, and the vector solution, or you know what, in Calc 3 we've been calling it r, so let's go ahead and write it as r. So that gives us a vector valued function r of t, which is given by 1/4 and then 1/8 1/2 of t, comma t. And what that tells us, this is the parametric equation of a line. So what that tells us is the original two planes that we started with, remember the equations that we wrote were two planes, have a solution, an intersection, and the intersection is a line that can be parametrized by this set of parametric equations, and then we solved our system of equations. Notice that in this case, since the line has infinitely many points, the system of equations has infinitely many solutions. And so that's how you do it, how you solve a system of equations by using matrices. All right, thank you for watching. That was a quick video. I just wanted to show you that. So thank you for watching, and I'll see you in the next one.